Hello, I'm Stefan Greber, project leader for LXD, and today we're going to be taking a look at LVM. So this is still in our current series reviewing the different storage drivers of LXD, and LVM is actually our oldest storage driver if we exclude the most basic directory type backend. It was introduced pretty early on, primarily because at the time we didn't really, Ubuntu hadn't really gotten into ZFS yet, and BRFS was not all that reliable, whereas LVM was pretty commonplace on servers, and figured that it would be a good idea to support that for LXD users on Ubuntu. We spent quite a bit of resources onto it initially. The storage drivers back in the days in LXD looked nothing like the way they do right now. There was effectively no concept of pools, so no ways to have multiple drivers concurrently. You instead just had to choose out of the box. It would be backed by directory, and then you could decide to switch to either LVM or in time ZFS as your main storage. That has then evolved into the storage driver mechanism we've got right now with storage pools and all of that complexity we've added. But yeah, it was very different back then. Now, what we made it support at the beginning was existing system with an existing VG using LVM on top of that to allocate a LVM fin pool, and then using fin provisioning to create volumes for each and every container on the system. It works in pretty much the same way as all of our other copy on write type backends, where each image would be imported first, and then the container instance effectively created as a clone of that. The main difference here compared to something like BRFS or ZFS is that LVM is block only. So to accommodate that, LXD will effectively pre-create a block device for every single image as a logical volume within LVM of a fixed size, and using ext4 as the file system by default, and then this gets cloned for every single instance. That works well enough. It does have some advantages. It's got very strong quotas because each and every instance has its own block device, which has a fixed size, and there's no way you can go past that. It does have some downsides. For example, turning something into an image, or doing copy between systems, or any kind of migration is quite a bit slower because there's no like nice file system aware mechanism to proceed with that. So for instances or for containers, we effectively use rsync for that, which is fast enough. For virtual machines, that's where things get really painful because there's really nothing else and we can do than replicate the entirety of the block device, which can be several tens of gigabytes large. So not necessarily ideal to run within a cluster or any of that kind of stuff. The other issue we had with LVM kind of over time has been reliability around its metadata mechanism, especially. They've kind of gone back and forth about like what kind of caching needs to be done, what kind of daemons you need to run to keep track of LVM metadata. And yeah, that got a bit tricky, especially because LXD often ships as a snap. A snap has its own file system, has its own version of LVM, which may differ from the one of the main system. And if they disagree about what's on disk or where things are on disk, you can get corruption pretty quickly. So that's been a bit of an issue. A lot of the LVM tooling we found is really designed to kind of install a machine once with whatever segmentation you want, and maybe resize things a few times, maybe create new logical volumes every so often. It's not really been designed with literally creating dozens of LVs every few minutes, as LXD can do if you're dealing with a lot of containers or a lot of virtual machines running on it. So that's why it's not really our top recommendation these days. If you do need some of those block features, especially like the very strong quota mechanism, the choice of whatever file system you want for the instance, that kind of stuff, then it's probably still your only option. But by and large, our recommendation tends to be ZFS these days. Now, as far as what we support from LVM, and that's kind of highlighted here in the doc that I've got open. As I mentioned, LXD by default will use fin provisioning. That's simply so we don't run out of disk space almost immediately. So with fin provisioning, it means you can effectively create more instances, more volumes than you actually have physical space on disk. that's pretty core to running something like LXD. But you can also turn that off if you just want to use very simple LVM with no thin provisioning whatsoever. You can do it, but you'll need to make sure you've got enough disk space for it. And that's kind of what we can see here. When you create an LVM storage pool, you can choose whether you want thin provisioning or not. And unlike pretty much every one of our other storage drivers, you can decide to use a dirty environment. That's because on a server, you are unlikely to have multiple disks with completely independent LVM. If you're using LVM, you're probably using all your storage within it, which means you might have a single volume group for your system and then creating logical volumes on top of that. If you want to use something like that, you're not going to be able to give a completely empty pool for LXD to work with. So that's why we've got the option to force the reuse of a otherwise dirty volume group, as in a volume group that contains stuff already. Don't do this like twice within the same LXD. The volume names are gonna conflict and you're gonna have a very bad day. But if the only volumes you already have on your LVM are system volumes that have names nowhere near what LXD is likely to be using, then you should be fine. You can also, in the thin provisioning case, you can do some amount of tweaking around the amount of metadata being used. The default usually works fine, but you can do it. The other thing you can choose is the name of the thin pool. By default, we use LXD thin pool, but you can change that if you like. The other options are kind of generic things for anything that's block-based. So as I mentioned, we're using rsync for container migration, and there you can choose if you want to limit the rsync bandwidth or what kind of compression to use. There are more LVM options on the volumes. That's what we can see here with control even for LVM striping. It's not something I've been playing very much with, but it apparently can really give you like a big performance boost for specific workloads. If you know how many stripes you want, what size of stripes you want, you can tweak that before creating a volume, for example, for a database. So we've got support for that. All right, that's pretty much LVM. So just go and play with it real quick. And here I've the usual server I've been using in this video series. This server doesn't have LVM out of the box. I actually suspect I don't even have the tools. Actually, I do have the tools, okay. So yeah, no PVs, no VGs, no LVs. So there's no LVM on the system. So we're not gonna be telling LXD to use an existing volume group because there's none. But if you just want to play with LXD on LVM, that's not a limitation. You can just say, yes, I want to create LVM, create a new volume pool. And again, you can use an existing disk if you want disk partition, or it will create a loop device. As I've done so far in this series, I've been using a partition on an NVMe drive. So I'm going to be doing the same thing here. I think that's the partition. And then just keep the rest as default. And that will get us a storage pool that's backed by LVM. Now, if we look at what happened on disk, you can see that now I've got a physical volume that's on the partition I gave it. There is a volume group that's defined, default, and the only logical volume that's defined is the thin pool itself, and we can see it's defined here. Now, if I launch an instance, this is gonna download the image, create a new LV with a default size, I believe it's 10 gigs, then we'll unpack the image, then do the clone from there. So if we go look at things now, we do have indeed a 10 gig image, 10 gig LV that was created to contain the image, and then the container was created from it. And that's gonna be ext4. So if we do go inside of the container, we're gonna see it does have a dedicated volume here. It shows it's 10 gigs large, and this is gonna be, I'm just gonna check, but I'd actually, yeah, it is ext4. So no big surprises there. Now, as mentioned, you can change that kind of stuff. So if we look at here and set block.file system, I believe, and say, I don't know, XFS. Is it on the volume? It might be on volume.block. Yeah, there we go. Okay, cool. And now use another image. Let's do Alpine. Okay. Oops, keep forgetting Alpine doesn't have bash. Okay, so it's mounted. We can see we're using dev default containers A1. And if we go look at the mount table, this time around, we are indeed on XFS. So that's one of the main benefits really of using something like LVM. You can pick exactly what file system you want to use. And LXD doesn't really care. It just creates a file system for you, handles resizing and that kind of stuff. But that's it. You've got very strong quotas in place because of the block not being able to go anywhere past its size. That's pretty convenient, but as mentioned, if you need to have like an optimized backup of one of those instances, if you need to be able to migrate them somewhere else, if you're doing like, especially for virtual machines, if you've got like a large virtual machine that you need to move somewhere else or publish or any of that kind of stuff, it's gonna be extremely slow. And again, there's a bit of a warning here. If you are running LXD on a machine that does already have LVM, you're gonna want to be careful. Either you give it a completely separate drive and you'll be fine, or if you need to have LXD play well with your existing LVM, the recommendation would be there's an option inside of the LXD snap that's called LVM external. We'd strongly recommend you set that to true and then reboot your system. That will force the LXD snap to use the tooling from your host system instead of its own copy. And that usually avoids a lot of the potential issues around the LVM metadata getting out of sync and potentially leading to data being overwritten or potential corruption. And that's it for a very quick look at LVM. It's not a very complicated backend. It's an interesting one because it's one of only two backends that we have that's block-based, the other one being Ceph. It's got some advantages that can be pretty interesting to some situations, like having properly separate block devices for every single instance is quite neat. That does come with the strong quota enforcement. It lets you do whatever file system you like, which can be pretty interesting since you can even do it on a per volume basis. Like you could create a volume for a database. It's a different file system from what you use on the rest of your instances. But it also does come with a bunch of downsides, especially, as I mentioned, around migration and publishing. But it also comes for things like you can't easily live update quotas. Given on some specific file systems, you can't even grow live. You need to actually stop the instant even for a file system growth. So there's a lot less flexibility around some of that stuff. But it's still a pretty interesting backend. And I think for those that are already quite invested into LVM and actively use that on their machines, that might be a pretty good fit. Hope this was useful. If you've got any questions, you can leave them below. Otherwise, go on our community forum, and I'll see you in the next one. Bye.